how are other jobs relating to it, right? And then you might use such a tool to quickly grasp, okay, there are many jobs that look similar, so maybe it's worthwhile to spend a lot of hours into it, right? So that's kind of the perspective that we thought is missing. Yeah.
Okay, cool. That's actually some nice work. And then we've got some 5 minutes left. If anybody's got any other questions, there's 17 people in here now. Anyone? Everyone's so quiet. Okay, so if there's no more talks, we'll get thanks, Julian, for a great talk. And yeah, we'll wait for the next person.
May I say one more thing, right? I mean,
yeah, sure, go ahead.
Yeah, so this definition of similarity that I mentioned in the talk, right? We found it really difficult, and we investigated many more metrics that I didn't show and many more different types of algorithms, right? So introducing 6 on this work that I showed you today. It's really difficult, right? What similarity means. And I really believe that, you know, the community must work together to come up and say, this is what we mean is meaningful in terms of distance between jobs, and that we have different distance metrics. And if you're interested in this, you know, to kind of come up with some more or less standardized expressions for it, you know, I'm really happy to work with you. Yeah, cool. Thank you.
Oh, thanks a lot. Okay, so we'll wait another three and a bit minutes until for our next talk. Grab a quick coffee. Okay, so my clock says 1:30, so that's 2:30 for you guys. So that's time for next talk. So we've got Jay Lofsted with a Stitch.io for additive manufacturing simulations. Melanie, if you want to start it. Yep. And guys, don't forget you can ask questions in the Q&A section here.
Hi, my name is Jay Lofsted. I work at Sandia National Laboratories, and I'm going to talk to you today about Stitch.io for additive manufacturing simulation. It's actually applicable for other things, but that's been our motivating example. The other people's names I have listed here, John Mitchell is a mechanical engineer that I've been working with. He's been driving the science side of things. Enzi Chen is a grad student that we worked with that helped develop the Stitch library in the first place. And then Manisha Ganesh and Gavin St. John are two undergraduates that we've worked with that helped develop our digital twin example that I'll talk about as well. Just to give you an idea of what kind of problem space we're looking at, since this is a new kind of I/O library, is the motivating example is a kinetic Monte Carlo simulation. And the basic idea behind them is they want to look at a time evolution for processes in nature. And the example that we started with was a simple one, it was just welding. If we wanted to look at how the materials, the metals, behaved and with a welder through simulation, we needed some particular kind of simulation to do it, and this is the right kind. We've taken that welding example and expanded it to do additive manufacturing as well. And that's instead of plastic-based, it's metal-based additive manufacturing. Another example where this kind of I/O approach would be useful and helpful is if you're doing a finite element kind of simulation, and for example, you have a pressure wave just because you have a metal cylinder or a metal rod or something, and you hit the end of it, and you want to look at the way that that pressure wave goes through the rod. The reality is that as the simulation progresses, there is the location within the rod that all of the activity occurs as the wave moves from end to end within the rod, but the rest of the rod is largely silent. And because of that, you don't really need to do any simulation work there. There are others possible. At Sandia currently, where I work, there's been 3 new simulations that we've developed because of this new I/O capability. The reality is that because of how this I/O library works, we took things that were either not feasible or not possible before and allowed you to even run them on a laptop. So one example is that the metal caps that they put on fuel tanks for rockets, they do 3D printing of metal to generate those, but that might be a couple of meters across. And if you were to do a simulation where you have one element per micron, you're looking at a domain that's in the petabyte kind of range. And if you need to write that out for thousands of time steps, that's going to quickly exceed the capacity of any system that we have on the planet today. And with this kind of system, we can radically reduce the amount of storage needed, but at the same time, the computation time, if we were running on a big machine compared to using this method, will be the same or potentially even faster. So the question we started with was, since the computation is localized, this is a tiny piece of the compute. So if you can think about a welding example, it's just exactly where the weld point is. Then why don't we just make the I/O focus on that part and then provide ways to fix it up so that if somebody requests a larger portion of the simulation domain, that we can give them back something that's reasonable. So it really comes down to the ideas that are behind a lot of things like NoSQL databases, which are just lazy, minimal, and eventually consistent. So we don't care about what the entire simulation domain size is. We just say, tell me where this is in the simulation domain. And if somebody requests areas that haven't been defined yet, we'll return a no value present, much like NetCDF does for climate simulations. And minimal, meaning that we only write the little section of the simulation domain that has been changed since the last output. That kind of makes sense. And we don't ever try to enforce any sort of consistency in the system, and instead think that eventually something is going to make sense, and we rely on the simulation itself to keep track of that. That's one of the ideas I think that a lot of libraries can really take advantage of in order to gain some performance. So the big idea that was required to make this possible was the idea that when we want to read, we're going to provide an arbitrary region at an arbitrary time, and we need to be able to stitch back together what that actually looked like, even though all of the correct pieces for that are spread across multiple time steps in multiple different blocks. And that's what the stitching process is. If you look at current libraries such as HDF5, NetCDF, Audios, Exodus is a wrapper around HDF5 that Sandia uses, and there's multiple others. They all focus on having this entire simulation domain written out at every time step. AUDIOS is a little more relaxed about it in that it doesn't enforce it, but at the same time, it does assume that it's there. If you try to request data that was never written, you're going to end up with errors. In our case, we just say, okay, there's no data there, no big deal. The simulation that we started working with is called SPPARKS. This is something developed internally at Sandia, but it is open source, and you can get it from our website. And that's what we ended up working with. So some of the other changes that we did from a typical IO library, as with many of them, it's written in C, which is not surprising. That's a pretty popular systems programming language. But one of the things that John really impressed upon me was how much he likes doing ad hoc analysis work using a lot of the Python tools. And because of that, we made it have a full capability native interface for both C and Python from the very beginning. And that means that you could write a full simulation in Python and get the same level of capabilities with Stitch.io as you could with M1 written in C or C++ or anything else that could import the C library. There's both a serial and a parallel version, depending on what kind of use you have. In general, the parallel version is more used for a C or C++ code like SPARKS, and the serial version is more used for a Python code. And it doesn't matter if you use the serial or the parallel version to create the output in the first place, the other one can read it just as easily. It's more a matter of the kind of coordination that would occur while you're actually reading or writing. So, but the actual underlying file would be of no difference. So the main rule changes that we made beyond what I've described already is, one, we don't just require that global domain setup. We combine data from multiple outputs into a single output. So if you have an overlapping set of regions, and as you're moving across an area, and this is at time 0, and then time 1, then time 2, then time 3, then time 4, and you're going to request this whole region as what you want, and you'll say, give me everything that is no newer than time step 4, it's going to have to pull together all of those pieces, and it'll have to combine all of those together. And that's, again, that stitching process. The other part is that John tells me that it's more natural for the simulation to use floating point numbers for time, even though that does not make for good matching. And because of that, we allow some absolute and relative tolerances to compensate. A decision that I made because it seemed like it was workable, and based on some other experience I'd had with both some of my own work as well as with a student doing the Empress project, is that we're using SQLite as our file format. And the upside for that is I didn't have to write a custom encoder and decoder and searching and all those kind of things. But at the same time, it also offers me the ability to access that directly from something like Python or C without going through the API or even going through the command line SQLite interface. And that is something that means that the data is fully accessible even without the IO library. So that gives people the ability to go in and try new things out without actually having to extend the API. In addition to this global domain not being required to be set up, you don't have to write things chronologically. One of the things that John told me they'd like to be able to do is continue to write things progressively later in time, but whenever they wanted to initialize an area of the simulation, they would again just go back and write that at time 0. And so it was not any difference for me, because we're using a database, to go ahead and just put additional blocks in a different time step, and then using the queries, we could just order them. So there was actually no penalty for doing that. And because he wants to do online monitoring using Python of the C++ simulation, we made sure that you could do simultaneous writing and reading while that's going on. That way you can say, oh, well, how's it progressing? And look at the progress on the file from your Python program, even though the simulation is currently running on a C++ code. The schema is dead simple, as you might guess. We have a series of fields. We have our global values. We have our timestamps. And yes, I did abstract them out to integer values so that we could do some exact matching on them a little more easily with our database queries. But other than that, you just have your min-max corners for your blocks and your blob. And that's pretty much all we store. And the magic comes into the querying and the reassembling of the blocks. The API is dead simple. This is the entire API. I don't have all the parameters here, but you can see it's just a simple open, close, get and set a few different parameters, and then write block and read block. And it doesn't need to do anything else beyond that. There's some additional functionality that we're potentially looking at in the future, but right now we've not seen any need to go beyond what we have here. And everything that we've thought about doing, we've discovered can fit within this system without really any sort of difficulty at all. So here's an example of the welding simulation. So all of those, that random looking noise kind of dots, that represents a metal powder. And that teardrop shape that's moving across it, that's actually the laser, and that's called the heat affected zone. And you can see those large colored areas, and those are the grains that get created by the melt and then the resolidification. And each of those areas, I got the 3 illustrated at the bottom, those are considered a computational volume. So when we run the SPARKS simulation, we just run it on that one little area at a time. Then we stop it, we shift over to the next subvolume, and then run it again. So we would do the black area, then the red area, then the green area, and so on, shifting it over and running the simulation multiple times for each one. That way we only have that small amount of data as our entire footprint, even though we're simulating across this entire area. You can imagine this going from a 2D example, or really kind of a 1D example, to a 2D example in X and Y, or a 3D example using a 3D printing, additive manufacturing kind of thing, just radically how much smaller your data volume is going to be when you start trying to write things out, and how much less computational resources you need to be able to do that kind of simulation. To kind of look at the computational volumes in a little more detail, on the left side here, there's an example of the laser path, and then the rectangular area is the tail and the cap for the heat affected zone, and then you have the width. And then that's how it's going to move. And on the right-hand side, you have the blue, the brown, and the green. And you can see based off the arrows that it's going to be sweeping kind of up and down as it goes across. And it uses those computational subvolumes as the amount of space that it ends up covering. So this would be an example of a plus kind of shape. The red border is the perimeter, and the blue is the laser pass on the interior. You can see on the one layer, it's going in one direction, kind of a upper left to lower right, and then on the other side it's going on an upper right to lower left kind of thing, and that would be alternating layers to give you more structural integrity. Now the challenge is that when you generate these paths that the laser is going to run on using a standard off-the-shelf slicer from a 3D CAD model, you're going to get this unpruned path on the left. And the problem is that some of those paths, there's no laser action at all, so there's no point in running the simulation there. So instead, you can get rid of those and save some computation time. So that's what the pruned path is we've eliminated all of the portions of the the path that the laser would take where the laser's not turned on. And if we again go back to that plus example, you can see on the left we have that geometry. In the middle, you can see the overlap of all the computational volumes. And on the right, all of the area in the middle, that's all the kind of random noise, that's the only area where simulation ever occurred. And then the red area on the outside, even though that typically would be part of simulation domain that gets written out, that's area that was never written and is just no data present. And this is not one time step that created that, but a whole series of time steps, because again, we get that laser moving in a small area across this whole thing. So imagine having to write that whole thing, say 100 times in order to be able to get this kind of output out. And instead we wrote this small area, small different area 100 times in order to get that data out. So we saved a tremendous amount of data volume there. Another example we've been working with, just because it's a little bit harder, is a staircase. And you can see here, it's pretty small. These are sizes in millimeters. So it's about 5 millimeters tall by about 3 millimeters deep. And each stair step is about 0.5 millimeter high. And yes, that's incredibly small, but because we deal at a micron scale, we want to be able to do this kind of a simulation for our testing purposes in a reasonable amount of time. And here on the right and on the bottom, we have an XY and a YZ, I believe it is, example of the actual simulation in progress. And you can see that it goes in 4 different paths, the up, down, left, right. And you can see I got those listed out there. And again, we got the powder. And then as the laser goes across it, you can see that these different crystal, the different metal grains are formed. And we can see the actual creation of the piece in progress. Notice on the edge of the bottom picture, we have some overhang area. That's actually places where, because of the way the parameters are set in the simulation, we know that if it were to actually be printed that way, we'd end up with some errors and some weak spots on the edges. And that's something that we would need to change. And that's really the motivation for this, is that we want to be able to run simulations of building things using 3D printers rather than having to build and test. So we can build it in the simulation and test it digitally, make all of our changes until we get to what looks like a good configuration, and then we can do the physical print and see how things work in the end. So the way that we do this digital twinning process is we use just a standard CAD file that would be used by an additive manufacturing machine. We use the open source slicer code, and it goes through and takes that CAD file and generates a series of G-code commands. Then we take those G-code commands and split it into the different layers that are in your whatever your CAD object is. We prune them again to get rid of those places where the laser is not operated. Then for each of those laser paths, we create a computational volume, initialize that in our Stitch file, and then run the simulation on it. And that's just a whole bunch of small simulation runs based off of the structure I showed you earlier. And so in terms of the benefits, we can move something from, say, 1,024 processes down to 16. Basically, we go from a cluster to a laptop, or we might take something that we couldn't really do on 1,024 processes and actually scale it up to that size and be able to get the level of parallelism that works. The data size could be 1/64th of what it would have been had we used one of the other libraries, or potentially even smaller, depending on the amount of material that actually gets created as part of the output. The wall clock time for running the simulation over the entire creation of the object is going to be the same or even smaller. And the reason why it might be smaller is that even though we have the startup and shutdown time for the simulation, because the output is so tiny comparatively, we could actually save time and be able to run it in less wall clock time. This has been so successful internally at Sandia that some of the people have come back to me and said, hey, we need to get some performance improvements on it. And then when I find out what they've done is they have as many as 400 million blocks in their output file, and they're starting to show some creaks. So I'm going in and doing some tuning right now. The version 1.0 is available on my GitHub site. You can go there right now and get it. That's what the QR code is for. And I had a paper at IOPS this year. You can go and read that as well. It gives you some additional details, or email me. I'd be happy to answer your questions. Thanks for listening to my talk.
Oh, thanks, Jay, for a great talk. I don't see any questions in the Q&A. Does anybody else have any questions? No. Going on. I do have a fairly basic question. The whole thing is predicated on everything running locally, right, on one system, as opposed to completely distributed across multiple systems if you don't have enough computational time on one system to get your stuff done, right?
It can run on multiple nodes. I don't know if that's what you mean.
But those nodes don't have to be temporally located, right? They could be anywhere, and then you could stitch it all together afterwards. Or does it actually have to run together?
That's correct. So you could really run those jobs and move around your Stitch output file, or even merge the Stitch output files later, and do it just kind of piecemeal, depending on wherever you could get the work done. So yeah, you could actually split it across. We haven't actually run in that mode yet, but that's certainly something that could work and should work without any difficulty.
Okay, cool. Thanks. So if there no more questions, I don't know if Jay, if you want to say anything else, or wait, no, there's one Q&A question. Sorry,
Okay.
my bad. Where is it?
What are the other major challenges are there apart from the 4 edges? Okay, so the challenges that we've run into is that each element, so each pixel that you'd see in the visualization, depending on the scale that we want to run the simulation at, that either goes, we have 10 elements per micron, or we might have 1 element per 10 microns. So we have that kind of a 100x difference in the scaling factor. And that obviously is going to have a huge impact on the performance and the size of the output. And so we're trying to be able to kind of run things at a coarse grain, just kind of get an overview. And then as we go through and tweak the parameters, we try to look at how to make things work properly. The issues on the edges have been one issue. Another thing that we've looked at that has revealed some configuration problems is if we make the speed of the laser too fast, we don't get the right amount of melt, or if you make it too slow, it ends up penetrating too deeply into the material. So we can end up looking at how fast we can let the laser move, so we know how quickly we can make a part and understand what its material integrity is going to be. There's, I'm sure, an ability to control, let's say, the heat of the laser as well, but I don't know what those parameters are. That might be something that's a little more fixed. But those are basically any kind of the parameters that you would set in this additive manufacturing case for how the laser would work, or what its temperature would be, or the path, those sorts of things. Those are all things that we can play with in the simulation space and then look at the output. One of the things we have done is we've taken CT scans of parts generated with a metal 3D printer that we have on site and compared them against the simulation results, and they were basically the same. So we know that the simulation is generating something that looks like what is actually being physically printed. So we can now trust that doing further analysis on the simulated parts is something that will give us a good representation of what should happen with a physically printed part. I guess one other thing, one of the other challenges that has come up that we've talked about is consider something like a coffee mug that has a handle. And since that handle is disconnected for at least part of the build from the rest of the mug, how to handle or how to deal with having that disconnected area is something that is something we need to investigate. John's concerned that because it's not connected, there may be some issues. I'm looking at it and saying, okay, that's just a different part where the laser has moved and it has an area where it's active, and there should not be any difference. So that's just something we need to test, but that is a concern. We've also looked at the possibility of not using axis aligned bounding boxes for our different computational volumes. There is a little bit of waste since we might be going in a diagonal, as I showed in many cases, because the bounding boxes are not fully used. But at the same time, the performance advantages of keeping things axis aligned in terms of the simplification of the data access, I think it makes that more worthwhile. But that's something we haven't proven out doing any sort of testing. I know the queries to be able to look at box intersection for non-aligned boxes, non-axis aligned boxes, is much more complex. So that's definitely a concern if we were to try to do something like that. So I've been doing my best to keep him talked into, let's just keep it all axis aligned for now, and it'll keep things much simpler. So those are some of the other things that are going on, in addition to just we have several 100 million blocks, and the query time was taking obviously a bit longer than they were hoping. So I'm looking at how to decompose the blocks table into a blob table and a metadata table. So in other words, where the max and min corners are, and also trying to change the way that the query works so that I have better ability to use the indices that are within the database. Because right now I have to do a little bit of math on both sides of my where clause comparison. And if I get that down so that there's no math on one side and I can do the other math outside of the query, then I have something that I can do that should be just really a straightforward index search rather than actually having to do a little bit more work. So those are some of the things that I'm looking at now.
One more question from
Is version 1 ready for use on our home 3D printers? Yes, definitely. So the slicer tool is the standard open source slicer tool. The Spark simulation you can download from sparks.sandia.go, I believe it is. And we have the configurations that you can use. The digital twinning code is something we haven't released yet because we're not really done building and testing that fully. But if you want to, yeah, you can certainly try it out for your own 3D printers at home.
I have a question.
Yes.
Oops. Oh, okay. So really good talk, Jay. So have you looked at? I'm just maybe I joined late in the talk, but have you talked a little bit about the way you map these SQL queries to sort of the domain, or how do you have you looked at sort of related efforts like, for instance, Apache Arrow, to actually look at processing the data, or is that something that's still in the future?
That's still in the future. Haven't done that yet. One of the things we did look at was trying to use an R-tree index to try to do the block matching, but we've actually found that that is, while it does offer a simple matching interface, it isn't actually good for space or time compared to this kind of a simpler approach. Given that I'm now looking at hundreds of millions of blocks, that's something I may need to reconsider. But that comes into that whole tuning side of things.
Everyone seems to have gone quiet with regards to questions. Although knowing my luck, it'll pop up as soon as I say that. No, everyone's still quiet. Okay, thanks, Jay, for the nice talk. And we can all run off and get some coffee, although it's not quite the same anymore. Okay, and I think with that, we'll close the session. Thanks a lot for both speakers. And yeah, enjoy your next coffee. Okay, ciao.
All right, everybody, welcome back. This is our last session for the storage and IO track. And we're going to have two talks in this session. The first one's going to be from Gary Grider from Los Alamos National Labs. And he's going to go through a lot of the hardware, software, and IO and storage related challenges that Los Alamos is dealing with and using to try to help drive our storage infrastructure and state of the art forward. And with that, I will leave it to you, Gary.
Thank you. Can you hear me?
Yes.
Can you see my screen?
Yes.
Okay, thank you. So thank you for inviting me to give a talk. I'm sitting here watching it snow, so I'm sure it's different there. And maybe other people have snow falling at their places. So I'm, as Jay said, I'm going to give you a little overview of kind of how we're thinking about serving a broad community of simulation, in addition to, newer workloads like AI and ML, which is what the conference is about. And first I wanted to say that it's, most HPC sites weren't born before, after AI and ML exploded for this last time, or this latest time. Most of them were born doing something else. Our side, of course, was born doing simulation. And so this is really kind of a talk about how does a site start to contemplate doing, AI and ML mixed in with, other kinds of more typical workloads from HPC sites, and how do we start to plan for that, and try to do it in a new and smart way. And so that's what the talk is about. First of all, I'll cover a little bit of background, so that you have some background to go on, and then I'll cover that topic that I talked about. So we've been at this for a while. 8 decades of computing is a long time, and I've been there a long time as well. And you can see some of the various machines we've had back from when we, invented our own machines with Maniac, all the way to, putting in Crossroads fairly soon. We've got a D-Wave system that's, it's a quantum annealer, and our big machine that's really the NNSA's workhorse right now is this Cray Intel Trinity machine down at the bottom left. You can see Roadrunner and other kinds of machines we've had. The CM5 was kind of interesting. It was the first top 500 machine on the first top 500 list ever in 1993. And lots of Crays, of course, and other things. And Stretch, the Stretch Harvest project was done at Los Alamos NNSA. So we've been at it a long time. Just a little bit of background about the machines, so you get an idea of the size we're talking about. So Trinity is our premier machine, and like I said, the workhorse in the NNSA right now. It's 20,000 nodes, roughly half Haswell and half KNL, million-ish cores, 2 petabytes of DRAM, which makes it pretty unique in the DOE complex. Most of the DOE machines don't have this much memory even. I mean, this machine was put in 2016, and most machines don't have this much memory today. They're going for, way more GPUs and far less memory. And so this, if you want to run something really big, really the only place you can run it, frankly, in the DOE. It's got a 4 petabyte NAND burst buffer that we put on there, and I'll explain why we needed that in a little bit. It runs at 4 terabytes a second, about 100 petabytes of scratch, typical CMR disk file system, Lustre, a little over terabyte a second, and 60 petabytes of site-wide campaign store. And I'll tell you a little bit about why we did that in a little bit. And it's tiered, erasure protected, and I can explain that. And then there's just this 80 petabyte site-wide parallel tape archive that runs at about 3 gigabytes a second that we use. And so anyway, that's the storage hierarchy and the premier machine. However, like us in Livermore, typically we don't just have one big machine. We have, whole bunches of machines. And so you can see the list of all the machines we have. It's probably wrong because it changes, from quarter to quarter almost. But you can see that the new machines we're planning, Crossroads is a 12,000 socket Intel SPR. And that's about all I can say about it. And then Tacoma is a 1500 AMD realm system that we put in, which is doing COVID-19 research. It was part of the CARES Act, the US government funded to build machines to do COVID research on. So it's dedicated to that. It's about to get a bunch of A100s added to it when the A100 slot nodes are available. So a little bit about LANL's mission and how it differs a little bit from perhaps other sites. And I really like this slide. Gary Ciccopoli, who's now at NVIDIA, who was originally at Sun and went all over the place. Many of you probably know him. Came up with this sort of way to think about machines and workloads, and he came up with these axes of data flow complexity along left to right and up and down as control flow complexity. And this is really for the processor primarily, but and so I put some labels on what these quadrants mean, and what workloads work well in these quadrants. And you can see that capacity jobs like what we do here, UQ jobs and things like that, and weapons engineering jobs and the like fit pretty well up in the standard processors. And the cloud, of course, lives up there as well, primarily. And then in the bottom left-hand corner is kind of where UQ, weapon science, and machine learning things fit. It's not terribly complex data flow, and it's not a terribly complex control flow. In the bottom right, of course, is edge IoT. So it's not complex control, but the data flow is really what it's about. So you see FPGAs and things like that down there. And then up in the right-hand corner is kind of where we live. We live in this multi-physics, multi-resolutional, multi-link scale, 3D unstructured sparse world. It's a mouthful, but that's where we live. And our jobs are really complex. And the reason they're complex is because of this multi-physics, multi-resolutional stuff. The memory footprints is so sparsely represented and so scattered and indirect that memory references are just a bear. And so we have a hard time getting high percent of peak out of our machines. Our applications run at maybe 5% of peak if we're lucky, usually more like 1 or 2% of peak. And on GPUs, they run maybe a 100th of that. And so so we don't see a whole lot of GPUs at Los Alamos, and that's the reason why, is because the GPU is really super good at lots of threads of fairly simple flows. But when you're doing misses and skipping around in memory all the time, they're not any better than anything else. So that's what we struggle with. And the other thing you'll find interesting about our kind of workload is that we run really, really big jobs. So that 20,000 node machine, we ran a job on it, and it ran almost nearly half of that machine for about a 6-month duration, and that was to get one answer. And that's a long time to wait for an answer for a 3D run, but those are the kinds of problems we're trying to solve. And there's not very good solutions for that right now, but that's where we live. This is a little bit about that problem, or those kinds of problems. We think of this is the way we think about it: the complexity of the problem and how many months or years is it going to take to solve it. And you can see that that we're living today in sort of months, and we want to get to these higher complexity problems that, if to use today's technology, would take years to solve. And the problem with that is it doesn't enable human learning. When you get a decent result in a year, it's hard to talk to your collaborators about it. It's hard to have a meeting once a week over coffee and talk about your problem and tell them where you're at. So it's really difficult to work in this environment, and we're working hard to try to change that. At any rate, as I mentioned, that big problem that we ran was nearly a petabyte of DRAM on 10,000 nodes for about 6 months. And it would be nice if we could get that down something like 6 days, which means we have to move up by about a factor of 30 in efficiency, and hopefully before we buy our next machine, which is a grand goal, and hope we get there. A little bit about our storage tiers. So there's the big machine up in the left-hand corner. And we have all these other machines. The big machine has its own private scratch and burst buffer, which I talked about before. Then we have all these other machines that sort of a global set of scratches and campaign store and home and projects and archive and things like that. And you know, this is something you probably all know, how today's storage arrangement is sort of the big compute fabric, sort of PFS router service kind of nodes, and then PFS servers on the edge. And this is where we're at. This is certainly not where we want to be, and we certainly don't think that we'll be able to live in this space for very much longer. So our next machine hopefully won't look much like this. So this is getting into the crux of the talk. So I said that you know, HPC sites really weren't born as AI and ML sites, and so we've sort of started trying to think about how would we think about, you know, a workload that's more mixed than we're used to. We're used to doing the simulation science stuff, you know, most of our time, and we still will be doing that, but we see more and more uses for AI and ML in science, and typically the use cases aren't nearly as big as our simulations, and maybe never will be. It's hard to say, but we, you know, we do need to find a way to service that requirement and that need for the science community doing weapons science and weapons management at the lab. So we started trying to write down attributes about, you know, simulations and how it compares to AI and AI training and graph analytics, and of course other sciences that we're familiar with, the bio and MD and the like. And this is the table we came up with. This is courtesy of Brad Settlemeyer. And he, you know, put this table together, and you can see that the differences in size, in sort of elements, and number of keys is the way he thought about it. He thought about this in terms of, if you thought about this as a key value, each one of these things is a key value paradigm, which they aren't necessarily, but if you did, this is how it would turn out. The key value interface requirements, you can see that simulation is lots of bulk inserts with range queries, with a few point queries, where say AI models is really more of a, you know, a single read update with bulk updates and bulk retrieval, and AI and graph analytics, of course, is low latency everything, and what they look like, job scales that we think we would see if we were doing these things at scale for us, and then the precision, of course, is important too, right? Because the simulation is almost all, if not all, double precision, where AI models, you know, sometimes can be 16 or 8 bits, and graph analytics, of course, is integer work for the most part, at least the things that we do. So anyway, this is the way we started thinking about the problem and how we were going to attack it. I took the liberty of putting that on a you know, quadrant oriented chart. I thought a good way to think about it, and you know, put graph analytics, of course, at the top with the IOPS over there, and simulation, of course, way over on the side, throughput and AI models, which, you know, seem like they're pretty hard to deal with, where it, you know, over quite a bit of IOPS and quite a bit of throughput and so forth, and AI training down lower, mostly throughput. And then I started thinking about how are we going to solve these problems, and we've recently started working pretty hard on trying to exploit NVMe, because NVMe is a growing $50 billion business, which almost is the size of HPC business itself, and trying to figure out how one would do this. And our old workloads were of course throughput oriented or bulk oriented, and didn't really have any latency concerns. And so of course, then they were on disks, so you couldn't do latency if you wanted to. And so the storage stacks could be very thick, and they were very full of buffers, and they are. And of course, if you want to do these high IOPS things, you can't really use thick stacks with bunches of buffers. You've got to get all that out of the way, which kind of means that you need to move to a no server, no storage server kind of model. And it also it sort of indicates that you need to move away from no kernels involved. And so the thing that we're primarily working for and towards is to give users direct access to NVMe over Fabric zones, if you will, or parts of each flash device, and do it in a secure way, recalling back to the ANSI T10 OBSD days, where you could access remote devices securely, and do it directly from user space, which is you don't have the kernel there for security, so you have to do it some other way. And that's about the only way we think we're going to get the number of IOPS required to service these things. If we put a kernel and or storage server in the way, we'll lose. And so that's the plan. So we've joined the NVMe working groups and standards bodies, and we're one of the only HPC sites that's there. Mostly it's us in cloud. And we're actually making some headway towards making this occur. We think we'll try to do a demo sometime in spring for the SNIA community, to show them that HPC has some interesting use cases in this space. So anyway, that's with that background, and you take this graphic and you look at the kinds of things that NVMe could do for each one of these workloads, and of course NVMe key value gets you lots of IOPS, and you can do single and bulk puts and gets and the like. And NVMe computational storage is what CS stands for, is really for throughput, so you can do offloaded pipeline erasure, compression, encoding, and the like. And why would you want to do that? Well, because storage server bandwidth is so horrible that you need, and even client memory bandwidth is so horrible that you can't do all these things at full network rate anymore. So offloading these things makes a lot of sense. Doing it in a standard way using NVMe computational storage standard seems like the right thing to do given NVMe size. So that's what that means. So anyway, this is the way to think about it, and working towards getting the standards bodies and products coming down the line to help us solve problems in this way, the way I talked about with user space, direct access to NVMe, and in computational storage NVMe. So the dream use, this sort of my dream of how I think about how you would use such a thing, is job scheduler, orchestrator, whatever you use, would get the requirements for the app, which can be provided in the job control. Do you want blocks? Do you want KV? Do you want object? What do you want? And job scheduler allocates or accesses maybe 10,000 or 100,000 zones scattered across thousands of devices that are NVMe over Fabric, gets a security key for them, gives that key to the application along with where they're at, and then the job schedulers scheduler restores any needed data from lower tiers up to that that set of zones, because we're forced to live in a tiered world because of economics. And then the parallel application launches with the keys for access. It uses user space directives to get to and use that. So user space file systems, user space key value stores, space block things, whatever it is, so that we don't have a kernel in the way and we don't have a server in the way. And then parallel application exits, job scheduler cleans up the zones, migrates to lower tiers and so forth. And so this is what we're hoping to enable, say 5 to 6 years from now, at least for some workloads. and you know, maybe in 10 years for all workloads. To accomplish some of this and other things to try to get to this, you know, 30 times improvement in efficiency for our codes and our workflows, we've banded a bunch of people together that all agree we need to work in this space, and this is that community. And I don't have the picture of CHPC on here, but it should be on there. And then this is the areas of interest that that community is interested in, and you can see it's a broad set of things, mostly focused towards trying to get higher efficiency for workloads of true interest and not just benchmarks and the like. And so that's what this is about. And if anybody's interested in collaborating and banding together to work, you know, work with vendors and convince vendors to do things, work with standards bodies and convince them to do things, such as that NVMe thing I talked about. That's what this body's about. And then I'll wrap up, since we need time for questions, with this. Ask me anything. I'm an old person that's been in storage, you know, for 35 years. And this is a sort of a laundry list of projects we have going on in storage at LANL, and or anything else that you want to ask me. I've left plenty of time for questions. Hopefully there'll be some interesting. So that's it.
All right, thanks, Gary. That was a very interesting overview of all the things that are going on and where you think things are going and where they've been. We don't have, oh, we do have a good question to start off with. It says, Happy Satole is saying, thank you for your talk. Is the campaign storage linked with all the HPC systems at LANL?
Thank you for the question. It isn't exactly. That's kind of not the way. That's kind of not the way it works. So the way our site works is we have this. You can get, you know, all systems can see all Scratch systems. All systems can see NFS file systems, but all systems cannot see campaign or archive. And the reason for that is neither are really great for user interactivity. They're you know, cooler storage tiers. So things have been packaged up in efficient ways to work on disks well, cheap disks. It's erasured multiple ways, so it has a 2-tier of erasure so that it can withstand interesting failure scenarios. I'll talk about that in just a minute. So what we do is we have a clusters that's job it is to move data from tier to tier or from scratch to scratch or whatever. So part of your and our job scheduler system is set up so that it's you can, you know, submit a job to any queue from any machine. And one of the things that it can do is ask that cluster to move stuff around. And so that cluster's job is to move stuff around petabytes at a day, certainly more than that some days. And so its job is to move to state to and from various places, and it can be done on demand with commands, or it can be done with scheduler, or it can be done with scheduler directives. And so anyway, that's the way it works. The campaign tier itself was done primarily because these 6-month and year-long runs that are happening, people need to save that data for about a year, and they don't need to save it all. Some of it's just restart data, but they need to save some of it because they may decide 3 months in that they need to back up a month and go in a different direction. And so they need to save, these things generate hundreds of petabytes or more of data in their lives. And we need to hang on to some of that data longer than days and longer than weeks or months, which is kind of how long data sits on our scratch file systems. And so campaign is really about keeping some of that data around for far longer, years and not decades. That's where archive lives. And so we thought we needed to put erasure in that was far more capable than any other erasure we'd been able to get our hands on. And the reason we thought that was true is because we were starting to see what we call correlated failure events. Most research done in failure, is sort of a random incidence rate kind of, most bathtub curve oriented studies. And we see that. That's certainly something we see with our, hundreds of thousands of disk drives. But what we actually see that's more worrisome is really bad days. And we had one bad day where we lost 413 drives, and that's a lot of drives. It's not a lot of drives compared to the population, but it's a lot of drives. And it wasn't, and because we could protect against stuff like that, and it wasn't one row, and it wasn't, there wasn't really the reason, the pattern that took out those drives was, it happened to be that we were using a whole bunch of drives all at the same time, thousands I imagine, and those happened to be, being written to when there was a brownout, in another county. And anyway, it was a bad day, and we were able to recover most of that, but it scared the hell out of us. And we were actually talking to other large sites, and they see similar things. They call them anomalous things. We're starting to think that they're not really anomalies. And they worry about that. Things like you shut your data center down and it goes cold for a few hours while you're doing something really, really big once in a while. And then most of the disk drives don't start back up right, and the like. And so anyway, these bad days is what we wanted to protect ourselves against. And so we went to this 2 tiers of parity. And so our configuration is a 10+2, and then underneath that, each one of those stripes is a 17+3. And in most of the rebuilds happen at the lowest level. And then if you have one of these really super bad days, then you can rebuild at the higher level. And so anyway, it's a little like multi-dimensional parity, which was done, before. There's been a paper or two about that. And there's actually a paper done that does similar things for trying to keep in-memory databases alive for years, or, months and months and months, if not years. And they're using similar techniques. And so at any rate, it's really interesting research. The way we gauged our ability to do this well was we wrote a simulator that simulated correlated events along as many dimensions as you would like to correlate on, and it would throw errors out, and then we could throw those errors against, simulators of RAID systems, and we could, determine if we'd lost data or not, and when. And what makes us a little unique in that regard is that our files are so damn big, think a petabyte roughly in size for a file. If you lose 1 byte of that file is no good anymore. You've lost a petabyte. And that makes us quite a bit different than the cloud. Their objects aren't nearly that big. In fact, many, many orders of magnitude smaller, like a movie, which is maybe 60 gigabytes, and we're talking about petabytes. So, 6 or 7 orders of magnitude difference. And so anyway, we went to this protection scheme because we couldn't find a product to buy that did it or did something better. But again, it makes using it very, not friendly to users. It's disk-based. We'd like to get to the point to where users and applications only touch flash or above. They never touch disk, because disk is getting worse and worse and worse, and it will continue to do so. And we'd like to hide that. So that's why we put this movement cluster in between the user and their data. We have a question about Intel FPR. Are we still on time for deployment? That's an interesting question. So Crossroads has been an interesting saga. We did an RFP a long time ago, back in it's been, the first one was like 3.5, 4 years ago. And we got bids, and we picked a bid, and we started negotiating with a vendor, and they pulled the product out from under us, and we had to start over. So Crossroads itself is not on time. It's 1.5 years behind schedule because of that mishap. Why do you think that happened? Well, it happened because if you look at our workload, remember I said that we don't have a lot of GPUs. It's hard to buy a system does flops that will do our workload very well. And so we have a really interesting way to buy these things, and we essentially give them applications that aren't our applications, but they're as close as we can get to them from how they work, on the machine's point of view, and still be unclassified. We tell them, the vendors, how much of those different applications we'll use by percentage in the life of the machine. We tell them roughly what the IO workload is going to look like for those applications, and they're then encouraged to take those mini applications, those surrogate applications, and modify them in any way they want, as long as they still solve the problem, and keep the the algorithm, be true to the problem that's trying to be solved. So they can change it any way they want. And essentially we look at how much improvement they got from the changes they made, and how much effort it took in those codes to get those changes made. And we reflect that onto our code base, and therefore we know if we buy this machine, it will take this much effort to get this much value add out of that machine. And GPUs have never won those wars at all, and they've been off by an order of magnitude since the beginning of time. And we hope that changes, and that accelerators start to get broad enough to work on our workloads. And remember, you can change the code any way you want. And so the number of bidders drops off pretty radically when you're not buying something super popular, which is bad for us, but it's what our workload is. And so anyway, that happened to us. We put out a new RFP. We got new bidders. Intel, the SPR won that bid. Your question about is it on time? Thus far, it looks on time. I can't say much more than that because of NDA, but thus far, it's not terribly far off of what our expectation is. But remember, we lowered our expectation a year and a half because of this bid that backed out, mishap that happened. So Crossroads has been quite a interesting project, because we're trying to solve a really big problem. There's a particular problem in mind for that machine, and HBM memory is sort of required for that machine. There's kind of no way to solve the problem without that. The memory accesses would kill you, and we would never get the problem we want to run on it before the machine was retired. So we have for that kind of no matter what, or the machine won't be of any value without something that will actually solve the problem we're trying to solve. So unfortunately, we just have to put up with where the industry is and where they're going, and try to make the best of it. And it's been tough for Crossroads.
All right, thanks, Gary. There's another question in the chat, but we need to move on to the next talk. I'll let you look at it there and answer that. But thank you for the talk. Our next talk is from Carlos Maltzon. He's going to talk to us about a buffer bloat and the impact we may be having on our storage performance that we may not be fully aware of.
Hi, my name is Carlos Maltzon. I am an adjunct professor of computer science and engineering at the University of California at Santa Cruz. My talk today is about managing buffer bloat in storage systems. This project is a collaboration with one of my PhD students, Ismail Mirvakili, and is very much still a work in progress. Funding for this project comes in part from the National Science Foundation, including the Institute for Research and Innovation in Software for High Energy Physics and the Center for Research in Open Source Software. I thank Jay Lofstead and the organizers of CHPC for giving me the opportunity to present here. I want to thank you for your attention to my talk. Before I start, a few words about myself.
I've been at UC Santa Cruz for 16 years, including 12 years as faculty, during which I've graduated 9 PhD students and 10 master students. I work mainly on programmable storage systems and practical reproducibility. In 2005, I became a co-founder and key mentor of Sage Weil's Ceph project, which is today a widely used open source distributed storage system. In 2015, I founded the Center for Research in Open Source Software that bridges the gap between student work and open source software projects. First, the background for the talk. Scalable storage servers consist of multiple parts that communicate asynchronously via queues. There's usually a front end that queues access requests from storage clients and uses one or more threads to forward queued requests to a backend. The backend queues these forwarded requests and batches them to efficiently use storage devices it manages. Storage servers can have multiple kinds of backends with different design assumptions about the underlying storage device technologies. These include disks, flash, but also computational storage devices with completely new storage abstractions. Batching in each of these backends is designed to reshape workloads so they use particular kinds of storage devices efficiently. Requests are scheduled in the front end to ensure different levels of service for different classes of requests. For example, requests that are generated by data scrubbers working in the background generally have a lower priority than requests from an application. While batching is device-specific, scheduling is not. So system designs that can add new backends designed for new storage devices favor a separation of scheduling and batching. The scope of the project is therefore to have the scheduler reside in the front end and to explore designs for backends to dynamically control the admission of requests depending on continually changing workloads and storage device technologies. Scheduling in the front end and batching in the back end work best if there are enough requests in the respective queues. This raises the question, what is enough for the front end and for the back end? The restrictiveness of admission control has implications on throughput and the ability to meet scheduling objectives. If there are, for example, too few requests in the front end, but more than enough requests in the back end, the system might work well in terms of overall throughput, but might poorly enforce scheduling objectives. This is because the scheduler, if only confronted with very few requests, has not much choice in deciding which requests to issue next. If there are, however, too few requests in the backend, then overall throughput and latency suffer no matter the scheduling objectives. If, however, the backend has the ability to admit just enough requests from the front end, but not more, throughput and latency of the backend is likely satisfactory. If there is enough work overall, the front end has enough requests to meet scheduling objectives. So the overall question in this project is, how many requests are just enough for the backend? The question is of practical importance. The open source storage system Ceph in its current implementation exhibits the problem of having too few requests in the front end radars, and too many in the backend, blue store in its case, because there is no mechanism to exert back pressure. The result is that any scheduler in radars is ineffectual and prevents Ceph from providing differentiated services that become particularly important with the advent of computational storage. Su Liang and others in their OSDI 2018 paper have identified similar schedulability problems in other storage systems, including HBase, Cassandra, MongoDB, and Riak. They provide a framework for identifying causes and proposing mitigations. The solutions to our schedulability problem is to move request scheduling from the front end to the back end. We are interested in exploring designs where the scheduler remains in the front end. The problem of backend admission control is the problem of determining the right capacity of the backend queue at a particular time. As long as the backend queue is at capacity, no more requests are admitted from the front end. The right capacity is dependent on the types, sizes, and the mix of requests on the backend queue. Generally, in real workloads, the mix is continually changing as new requests are admitted and batches of requests are sent to storage devices. The key challenges are the following. What is the signal for the capacity of the backend queue to be too large? Can the signal be based on metrics that are easily computed without slowing down the backend? How often should these metrics be evaluated? Given a signal, how much should the capacity be reduced? How should the capacity be increased if there is no signal? How can the backend self-calibrate for any workload and any storage device technology? The problem described here has an interesting parallel to the problem of buffer bloat, found in packet switches and first described in 1985 by John Nagel. To minimize packet loss, packet switches increase their queuing buffers. However, TCP relies on packet loss as a signal for congestion. The fact was that TCP flow control degraded and latencies of wireless connections increased significantly without increasing throughput. To mitigate buffer bloat, Ben Jacobson and Kathleen Nichols developed controlled delay, or CODL, an active queue management strategy to drop packets earlier to keep feedback tight. The algorithm measures the latency of each packet in a queue and determines the minimum latency over a time interval. At the end of the interval, the algorithm compares the minimum latency to a target latency. If the minimum latency exceeds the target latency, the algorithm drops a packet and shortens the measurement interval length by a fraction of the previous interval length. Once the minimum latency does not exceed the target latency, the algorithm restores the algorithm measurement interval length. Packet loss is the signal for TCP for network congestion. We mapped buffer bloat and its mitigation by CODL to backend admission control in the following way. Buffer bloat maps to the lack of back pressure in the backend, leading to excessive queuing in the backend while leaving too few requests in the front-end queue to have effective scheduling. Coddle's trigger for packet loss maps to the signal for the backend queue capacity to being too large. TCP window size management maps to feedback heuristics in admission control. Coddle applied to networking is parameterless. That means the interval length of 100 milliseconds and the target latency of 5 milliseconds that are inherently built into the Coddle algorithm as used in the networks has shown to work well over a large variety of network traffic and environments. Preliminary simulations showed that Coddle can be used to signal excessive queuing in the backend. But it also demonstrated that the Coddle parameters like target latency and interval length and the strategies on how to decrement and increment backend queue capacity are sensitive to types and sizes of requests, their mix, and the storage device technologies. As I mentioned, this is still work in progress. We've created a simulator for Brewster with a latency model for 4 kilobyte writes to SSDs. We used the simulator to deepen our understanding of the effect of feedback heuristics, and we designed feedback heuristics that seem to work well. In particularly, we used just like TCP, we used multiplicative decrease if the backend capacity is too large. And we used additive increase if we don't receive or if there's no signal that the capacity is too large. This is, again, very similar to TCP. We also found that we found the best results when the multiplicative decrease is based on the distance between measured minimum latency over an interval of batch processing and the target latency. We ran the simulator with and without Coddle using different target delay intervals and IO depths. IO depths is the number of requests in flight and is determined by the workload generator. We assumed that a reduction of throughput of no more than 10% is acceptable. We found that for our test environment, Coddle target latencies and interval lengths that are 2 orders of magnitude smaller than what is used in networks works well. For instance, a target delay of 300 microseconds and an interval length of 1 millisecond and an IO depth of 48 achieved a 45% drop in queuing delay and a 10% drop, while also causing a 10% drop in throughput. This is right at the edge of what we deem to be acceptable, but the 45% drop in queuing delay means a significant number of packets remained on the Rados side, and a significantly smaller number of requests are in BlueStore, thereby increasing the ability of the front end to schedule effectively, and while still having acceptable throughput in the backend. Similarly, a target delay of 500 microseconds and an interval of 1 millisecond again with an interval of 1 millisecond and an IO depth of 48 requests in flight, led to a 25% drop in queuing delay at only a 6% drop in throughput. Again, it shows that there are plenty of choices here, and that CAUDL is indeed effective in balancing out the requests between the front end and the back end. The next steps. We are now in the process of validating our simulations by prototyping in mission control and CAUDL and BlueStorm. The next step is to find CAUDL or maybe another active queue management strategy. We're still open to other strategies, and we might be also finding completely new strategies that work over a more diverse workload than just 4 kilobyte writes. Another next step is to automatically calibrate CAUDL for specific storage devices. Or again, maybe another strategy of active queue management. I'm happy to take questions. If you want to have further discussions and contact us, please look me up on people.ucsc.edu/carlosm.
Thanks, Carlos. That was a really interesting talk showing that we do have some hidden places in our storage system that we may not think about that are causing us potential performance problems. Give it a second to see if anybody's got any questions that pop in. Okay, we don't have any yet, so I'll go ahead and ask a first question. One of the things that popped into my head as I see that you're pulling the scheduling to a different part of your storage stack is there was a push many years ago from some of the large vendors like Google, I think was one of the big people saying, please take all of the intelligence out of the drive and just give us raw spindles. Does this really kind of fit into that same kind of territory where you want to take the control out of the devices themselves and kind of pull it up and so you can have better control over your devices, or is this really a higher level scheduling kind of setup?
It's really a higher level scheduling kind of setup. So the problem that we're seeing is that a lot of storage systems in the past try to, basically assumed that the storage devices are slow, right? And Ceph is one of those where you could just rely on the fact that things would just pile up on different levels, and the levels that we're dealing with storage devices would just be slow. And so then scheduling wasn't really that much of a problem. Now as storage devices become much faster, you have to really balance out your need for scheduling and for the need for actually, making the throughput possible for these faster storage devices. So it's really a much higher level concern than looking at storage device themselves, but it's triggered by faster storage devices.
Okay, we got a question in the Q&A. To put it simply, it just says software-defined storage.
Yeah, so not sure exactly what that refers to, but remember that this is really the talk was really about the storage server. Now I think the question, I might interpret the question unless there's some clarification as to how you might change the policies in a storage server to deal with different workloads. And that is certainly our outlook is to, by solving this problem, we might get really valuable statistics about the behavior of storage devices that we can, propagate to the upper levels of the storage server or the front end, including the scheduler. And so scheduler might be able to predict. This is, for instance, important for reservation-based scheduling, predict the behavior of certain requests, and so might make more intelligent scheduling strategies possible. So in that sense, yes, I think it is relevant for software-defined storage. But I think you know, right now we're just looking at sort of the very basic question: how do we keep as much of the request queue in the front end of the storage server as opposed to the back end, where we typically don't have scheduling in place, right? And so that's sort of the scope of the project right now.
Okay. So we don't have another question, so I'll ask another one since we got another few minutes left here. With the Meerkat radio telescope, they have basically a constant stream of data coming in, and they're using Ceph for their back-end data storage. In a situation where where you have this constant data stream coming in rather than a varying workload, would this kind of come into play, or is that really more you just need to have the right balance of hardware capacity and bandwidth capacity?
I think it will always come in because you're always going to have also sort of these maintenance storage workloads. So this is really the use case that we're targeting. First is a fundamental one where you have a jobs, you know, you have the actual workload, the production workloads, but then you have also these maintenance workloads that are actually generated by the storage system by itself, like scrubbing, for instance. And so you want to make sure that scrubbing, for instance, is always lower priority than the production workload. And that's not possible if you don't have, if the scheduler doesn't have actually the alternative between different, it doesn't have a choice in scheduling one request over the other. And so, and remember, this is not, the problem is not that there is not enough workload. The problem is that currently, because there's no back pressure from the backend, workload gets just forwarded, you know, as fast as possible. And so the queues in the front end are almost always empty, while the queues in the backend are completely bloated, right? And so so the immediate reaction you have, well, why did you just limit the queue size on the back end? Well, it turns out that's exactly the question that we're trying to solve here. If you just take a constant, then you're running into problems that you might limit throughput for some workloads, or you know, it might be okay for some other workloads. But it's fundamentally, I think every storage server has to deal with multiple workloads. And that's only getting worse if you know, as you have more kinds of devices, as maybe the devices become more intelligent, as you have to, you know, maybe you have new storage server abstractions, so you have a greater variety of things to deal with. Maybe you want to have quality of service, more you know, kind of more guarantees of the storage system. In all these cases, you have to fundamentally solve this problem of schedulability that allows to keep enough work on the front end so that you can schedule intelligently.
Okay, good. So we don't have one question, so I'll ask one last one in the minute we have left. I know this is not something that's unique to Ceph. Do you know if any other file systems or storage systems do a better job of managing this, or is this really just a universal problem that you're addressing in Ceph as a first target?
Well, we're using Ceph as a prototyping platform, but as I said in the talk, there is evidence from Suli Yang's paper, right, that this is actually a pretty widespread problem.
Yeah.
And the reason why this problem is, and usually the way, and I think the way Suli Yang is addressing it in her thesis is in her her OSDI paper, is that that you just move the scheduler to the back end, right? To just add another scheduler, and that's, you know, we're trying to avoid that. So I think we're hoping that what comes out of it is something that a lot of storage systems can use.
Okay, great. All righty. With that, we're out of time. Thank you, Carlos, and for a great talk. And
thanks, everyone.
We now have a 15-minute break, and then back in the main event hall, I believe it's called the keynote session. You can join the keynote, and that will be in 15 minutes at 16:30 South Africa time. So this Zoom will end, and we can pick you up there. So see you all there. And thank you for coming.